with neural nets, which are really the foundation of everything else I'm going to talk about. I like to give everyone a fun challenge. Let's imagine that you have to build an algorithm that can distinguish dogs from cats. Think about if you did this in a rules-based way, what are the rules that you would pass into this model in order to teach it to recognize an image of a dog from a cat? You'd probably say things like whiskers and pointy ears and size. And the truth is, for decades, computer scientists like myself used to build computer vision models in a rules-based way. And when we did that and we applied those models to new data never seen before, those models were only about 60% accurate. You know why? Because there are lots of big cats and small dogs, right? There are a lot of corner cases that you can't account for in a rules-based approach. And if you think about it, how does an infant learn what a dog or a cat is? You know, you don't tell it rules, it sees lots of examples and it learns for itself what a dog or a cat is. And so we took that knowledge and we built algorithms by allowing them to learn for themselves. So we take this brain, it's effective, it's a neural net, and it's has lots of interconnected nodes, and you feed it thousands or tens or hundreds of thousands of images of dogs and cats along with their labels. And when that neural net encounters new data it's never seen before, that's when it's able to get about 98 or 99% accurate. Why? Because we're not constraining it by human rules. We're allowing it to learn for itself from the patterns that it sees within those pixels. So you can feed it images of cats and dogs. You could also feed it images of chest x-rays. So Stanford radiologists few years ago built an algorithm that's better at diagnosing pneumonia from chest x-rays than human radiologists. They fed it 50,000 images of chest x-rays. They said, this is pneumonia, that's not pneumonia. The algorithm's now better at diagnosing pneumonia than human radiologists. The developer of the algorithms that actually come out and said, hey, as far as radiologists are concerned, we don't need to be training anymore. And I think that's an aggressive statement, but the point is doctors spend a lot of their time looking at images and listening to sounds. Algorithms are better than humans at doing both of those things. I'd rather my doctor spend his or her time thinking about the patient as a whole. I don't know if any of you recognize these, but these are oil tanks, and the significance is they have roofs that expand or contract depending on how much oil is inside. When those roofs contract, they leave a shadow. The width of the shadow tells you how much oil is inside. So there are companies with satellites circling the globe taking images like this, and they can calculate with a high level of precision based on that shadow how much oil is in each tank, and they can aggregate that to figure out how much oil is in all the tanks combined. And that is information that then allows you to calculate the world's oil supply with a high level of precision. That's information that private equity funds, hedge funds find very, very valuable. So these tools are just that, tools to solve problems. There are companies, there's a company in Africa, they said, we have a problem with endangered species, hunting and poaching of them. So it took drones and armed them with cameras. It added computer vision software on the cameras. Those drones now follow endangered species around. When they see poachers, they notify the local authorities who come and intervene. So it's a really clever application of this technology that I, a data scientist, would have never considered.